Hello and welcome to the Machine Learning Podcast, the podcast about going from idea to delivery with machine learning. Your host is Tobias Macey, and today I'm interviewing Tapio Friberg about building machine learning applications on top of synthetic aperture radar data to generate insights about our planet. So Tapio, can you start by introducing yourself?
Sure. So hello everybody, my name is Tapio and I'm a machine learning engineer at ICEYE.
And do you remember how you first got started in machine learning?
Sure, it's quite pure gate theory, you know. So I was working in a lab for material science actually, I was working a summer job in there, and I was working on this laboratory equipment, and I was really bored. I was thinking that there must be a better way of doing this thing, and I started writing a script in MATLAB for doing the same experiments with image processing. I got super excited about that. Then I decided to do a minor in computational science. Later on, I did a minor in computational science in my master's phase also. And it turns out that I never did a single day of work in the so-called pure material science fields, even though I do have a degree in that.
And so in terms of what you're doing at ICEYE, I'm wondering if you can just describe some of the overall context and some of the story behind the company, or at least your involvement with it.
Sure. ICEYE is a Finnish-Polish aerospace company. It's dedicated around building and operating synthetic aperture radar satellites. So SAR in short. SAR, it's a technology where you use microwave frequencies and exploit the movement of the platform, which might be an airplane or satellite or otherwise, to create radar images. These radar images, they for the human observer, they kind of look like optical satellite images in the beginning, but they are quite different. Most notably, they are famous for doing really well in change detection, being able to detect metal objects quite well. So, for example, ships and airplanes. And also, with the radar imagery, we are able to image through clouds and through darkness. So there is no single time in the day or no weather conditions that we cannot observe. So, for example, we have imaged through active volcanoes, through the ash plume. We have witnessed extreme flooding through a hurricane. And we have observed during a multi-month cloudy season on the Amazon rainforest. And the company, it was founded in 2014. I joined the company in 2019 after the company had launched the first few satellites. And I joined the freshly formed analytics team to perform analytics on the satellite images.
And in terms of the analytics and the applications of machine learning, I'm curious, what are some of the problems that you're trying to solve or the types of questions that you're trying to answer with those ML applications?
So for me, machine learning is a tool of desperation. So you use machine learning if you cannot do it in any other way. Typically, this desperation comes from scaling. So the situation for us right now is that we have performed over 20 launches up to date, and we have a very large constellation of SAR satellites. These SAR satellites, they are taking images all the time, and each of these images are hundreds of square kilometers. So in that sense, for many applications, machine learning is the only way to do it. Of course, the human brain and the human eye is still much better than machine learning. So in some use cases, you still want to have an operator look at the images. But in many cases, if you want to observe or monitor or do persistent monitoring, machine learning is, in my opinion, the only way to do it. Of some particular kind of like applications I have worked on, I could maybe mention deforestation and flood detection. Both of them aren't really like super exciting machine learning applications, meaning that they're not cutting edge. They are typically just semantic segmentation. Deforestation is done over stacks of SAR images. So we monitor the same site and we take images between every day and every week. And then we run it through some kind of a model and create, for example, deforestation alerts from that. And then the flood solution is something that you opportunistically take acquisitions or images of flooding. You use machine learning models to refine this information. And then you don't do anything with that particular information, but you pass it forward to other teams and to other models.
And in terms of the source data that you're working with, you mentioned that it's synthetic aperture radar. It's being captured via satellites that are orbiting the globe at varying periodicity. I'm wondering if you could just talk to some of the ways that source data poses a unique challenge to ML applications, and maybe some of the ways that you have had to customize your solutions to be able to work on that data versus some of the kind of prior art that's available in the ecosystem.
I often heard that there's like a discourse about the challenges of Earth observation, and quite often the discourse turns into the amount of data. So everybody is saying that we have so much data, and it's always terabytes of data and hundreds of millions of pixels, and this and this and this. But I never thought of that as a real challenge, or it is a real challenge, but it's also the price of admission. So those problems, if you cannot solve those problems, you're already out of the game. So by definition, we have to have some kind of solution, and by definition, everybody else has already some kind of solution for that. So maybe your real question when you were talking about the SAR specific stuff and not only Earth observation specific stuff, I think the real problem is that we really can't like stand on the shoulders of giants as easily as the so-called traditional computer vision community. So when talking to computer vision people, nobody wants to train their own models from scratch. I mean, so everybody usually wants to use some kind of baseline model, and you can take an ImageNet and put it on some reasonable model and then fine tune it, and you get some reasonable results. But because of the SAR physics and the SAR image domain, you can use pre-trained models. You can use ImageNet. It's not harmful, but it's not very useful. So you cannot really bootstrap your processes of the other people's work so easily. There are no pictures of cats and dogs in SAR images or SAR images. Another kind of like subtle difference in Earth observation and then maybe traditional computer vision, that usually in traditional computer vision you have an image of an object. So if you take an image, it's usually depicting something. So there is like a car in the object, and because of that, there are some interesting features in the object. But if you take a satellite image and you turn it into patches, for example, something small enough that you can put through a neural network, there is no guarantee that there is anything interesting in any given patch. The opposite, actually. In most of the patches, there isn't anything interesting, just some kind of texture. There might be forest, there might be fields, there might be a single road going through. But the image isn't actually depicting anything. And this has very kind of subtle implications for topics such as self-supervised learning. So if you are doing self-supervised learning, you're augmenting an object, and then you're hoping that the model understands kind of like the latent space behind that and understands the things that make the object an object, even though you crop a part of the image. But when you're doing self-supervision and it's just a field or something, and then you're cropping a part of the field, you're not really changing the problem in a meaningful way. So in both self-supervised and semi-supervised domains, the augmentations have to be extremely strong, and it can be quite weird, the results, or unexpected compared to literature, let's say. And then, of course, there's the physics. So the physics of the problem, that's maybe the reason for why we cannot use transfer learning so easily, is because the physics of the problem is so different. So radar's backscatter is very anisotropic, meaning that if you change your look angle, sometimes even slightly, the features can change very strongly. So there might be like flares and like the backscatter intensity can go up a very large amount with a relatively small change of field of view. There's a very high dynamic range, so it's not uncommon to have 4 or 5 orders of magnitude difference between weak features and strong features. So working in a logarithmic space, that's necessary, but that's not enough. And then there's a phenomenon called speckle, which comes from our wavelength. So the wavelength in the synthetic aperture radar is typically in the order of centimeters, or typically, I think always in the order of centimeters. And because of that, you start getting these kind of like interference effects. And one of them is this called speckle, which causes the images to look extremely grainy if you are looking them at full resolution or at a single look, as we say. So this causes very high entropy in the images, which has implications on the dimensionality, of course, and it also breaks almost all old school image processing techniques, such as edge detection and such. On the other hand, there are some very interesting frequency domain approaches that one can take. So there is a huge amount of information hidden just below the surface.
In terms of what you were mentioning of the physics of the problem, the fact that you're collecting this data via satellites also brings in the question of the kind of level of consistency and accuracy as far as the kind of bounding boxes of the data that you're consuming, where on one pass you're collecting within a particular range of latitude and longitude, and then when you pass over that same space on Earth, then maybe the angle of direction of the satellite has drifted briefly, or like there's even a quarter of a degree of difference in terms of the latitudinal section that you're collecting. Maybe that causes enough variance in terms of the actual physical attributes that you're viewing that you have to account for those variances within the kind of matching of the time dimensional data that you're working on across a given geographical space. And I'm curious kind of how much of that variance you have to account for and how much of it is accounted for within the kind of data collection and data preparation stages.
Yeah, in my mind, there is kind of like two different ways that you can work with the SAR data. One is that you have this like opportunistic acquisitions, so you're doing multi-incidence angle acquisitions. So there might be something that we cannot predict, for example, a natural catastrophe, and then because we have a large constellation of satellites, there might be some satellite, not always the same satellite, looking at the ground from some direction during some time. And then you can gather between 1 and 3 of these images or even more, and then you need to make them fit in some kind of way. And that can be very challenging, and then you're working in only the amplitude domain, so you're only looking at the images and you cannot do any phase stuff. The other part where it gets really interesting is that when you have the so-called ground track repeat. So if you are able to image from the same satellite, and the same satellite is going through almost identical orbits when it's passing through the next time. So we have a temporal, in some of our test cases, for example, or in some of our cases, we have a temporal frequency of once per day. So we can have a satellite in an orbit where it goes over the same site every day in almost the same location. And in that case, you start gaining access to the phase information, and you get so-called coherent imagery. And then that becomes very interesting, and you can withdraw a lot of information relatively easily from there.
You mentioned that you're not able to stand on the shoulders of giants for a number of elements of the ML applications and the ways that you're working with that SAR data specifically. And I'm curious, in terms of the overall workflow that you are building and the ways that you are approaching the machine learning capabilities within the company, what are the elements that you are able to use off the shelf and some of the specific areas that you have to focus on custom solutions because there isn't any prior art, where maybe you're able to use some of the network architectures that are applicable to kind of image analysis and computer vision, but you need to customize them because of the fact that it's not purely optical data that you're working with, or maybe you're able to use some of the existing like feature stores and the typical kind of mechanical elements of the machine learning workflow, but you have to do a lot of customization in terms of the actual network architectures. I'm just curious if you can talk through some of the kind of off-the-shelf versus custom-built solutions you've had to work through.
Sure. As in most machine learning work, at least in the industry, the model itself isn't really the interesting part. So we like to use models that are proven. We like to use models that are a couple of years old and something that we don't have to reinvent the wheel. So we can just use models off the shelf in most of the cases. Of course, they behave differently. So we had some interesting results. For example, we had the DenseNet was performing better than the ResNet in some of the cases, and we never figured out why. But that's just a part of the job. Do a huge amount of experiments and see what happens, and try to keep track of that. The part that where we had to customize, that was quite a rough awakening for me when I joined the company. As I was thinking that I get to work on all of these cool machine learning applications straight out of the gate, like Kaggle competition. Here's the data, train a model. Didn't exactly go like that. So for example, the SAR image, we typically work in radar geometry, or so we work in a SAR geometry imagery, and that means that the x and y axis of the images, they are more defined in the sense of time than in space. And they have very weird kind of artifacts. They distort in nonlinear ways. So in reality, when I joined the company, my work was to start writing libraries that can do projections, so we can even get the labels. That labels are typically like latitude, longitude, so map geometry. And just to get the labels from map geometry into SAR geometry took me a surprisingly large amount of time. And that same kind of like thread has continued during the years and during many different projects. For example, I wrote this one library, and in this one library, I started wondering how much of this machine learning library is actually machine learning, and literally 90% was something else: pre-processing, post-processing, projecting. Then the machine learning part itself is just call a couple of functions and then you're done.
Because of the fact that there is so much extra work around the project of building the model, and the actual building of the network or building of the algorithm is just those few function calls, how much domain knowledge have you had to acquire since joining ICEYE to be able to be effective in understanding what approaches to machine learning, what network architectures are useful, what are some of the data processing steps that you need to do to be able to feed it into those algorithms, and just kind of the overall understanding of the space that you've had to build up to be able to then say, okay, I understand what I need to do and how I'm going to do it?
Quite a lot. There was quite a big threshold in the beginning. So the first few machine learning projects that we did weren't very successful. Partially because we couldn't scale them up enough, so we didn't have the processes and infrastructure in place to gather enough data, and partially because we lacked the domain knowledge to avoid all of the stumbling stones, and there were many stumbling stones. Luckily, in the company, we have a lot of people that have done a long career in SAR, and we have this like large roster of excellent SAR experts that we can use, even though we have people like me from a machine learning background with no previous SAR knowledge.
As far as the organizational aspect of using machine learning on this specialized problem domain, I'm curious what the kind of organizational structure of your engineering team looks like, kind of what the relative sizes of ML engineers versus data engineers versus software engineers, and some of the communication patterns and the kind of general team topology that you have settled on to be able to use these machine learning approaches to be able to figure out what are some of the features of interest as far as the problems that we're trying to solve for, whether it's the flood detection that you mentioned, or deforestation, or being able to understand property damage after wildfires, and just how the kind of organizational mission has been reflected in terms of that team topology and the relative focus of which strengths you need in which spaces.
Yeah, I don't want to go too deep into the team topology, but let's say that machine learning people, we do models, and models are not products. So what people want to buy is products. They want to buy something that is useful, and the raw output from a machine learning engineer is very rarely straight away useful. So we do have many teams, and they are collaborating quite intensely to create our products based on our models.
As far as the kind of productization of the analytics that you're producing, I'm wondering if you can talk to the operational requirements that imposes, whether you're doing largely just batch execution of, I'm going to process all of this data through this ML model to determine is there a feature of interest, and then pass that to a human operator to do confirmation, or are you doing more kind of real-time detection of every time there's a pass over a certain geography, I want to make sure that I can see, is there a feature of interest within this particular problem space that I'm addressing? Or if you're doing any sort of interactive inference where the ML models are being exposed through an API and getting fed certain requests or certain information to determine, yes or no, this is something that I need to care about.
That depends heavily on the product or that we're developing on. So that depends on what you're trying to achieve. Previously, I was talking about how uninteresting the amount of data is, but still, the minimum unit of data that we have is a couple of gigabytes. So if you want to use all of the resolution on the image, and if you assume a medium resolution image, that means that most of our jobs are typically batch jobs. So you want to do divide and conquer, you want to run it on the cloud, or you want to run it on batch jobs. We have done human in the loop, sometimes just to catch the bad cases and just to gather more training data. So if the model is young, we want to be sure that it's working as we think it will work. And then when it makes mistakes, we want to capture those mistakes to feed them back into the training data.
And as far as the training data and the labeling, I'm wondering if that's another area that you've had to do some sort of specialization to be able to streamline the workflow, where there are already pre-existing solutions for being able to feed in a large batch of image data and do bounding boxes and labeling of that of the various types of objects that you're trying to detect. I'm curious if any of that is applicable to the SAR imagery, or if it's something where you've had to build your own workflows around how to actually label the features of interest and be able to pick out the interesting aspects of the radar data to be able to have your ML models pick up on that and do the training.
Yeah, there's maybe 2 points I would like to raise. First of all, when you're just counting the area and the pixels, there's a very large amount of stuff that needs to be labeled. So if you want to label a single image, then you're labeling an area that might be, or a single frame of a single image, you might be labeling an area that's 70 kilometers times 15 kilometers. So if you're trying to click on every interesting thing on the ground, that gets very tedious very fast. Been there, done that. And the second part is that the labeling platforms, as you probably have noticed, there is really a gold rush going on, and a lot of people are selling the tools, because during the gold rush, the people that got rich are the people selling the shovels. But we had a lot of problem in finding a nice geospatial labeling platform. We haven't done a review in a while, but when we did, we found multiple platforms that did have a geospatial support to a limit, but then they were missing some kind of features. So we did have to end up writing some of our own solutions, which is, as an engineer point of view, I never want to write my own solutions. I always want to use somebody else's if possible.
Talking through the end-to-end workflow, you mentioned needing to be able to have this labeled data. You have your ML models that, as you said, are largely a lot of kind of data cleanup and data prep. I'm wondering if you can just talk to what that end-to-end process looks like for saying, okay, this is the feature that I'm trying to optimize for, trying to detect with this model, and now I'm going to go all the way through to delivering this model. It's being used in a production context, and kind of what production looks like for that particular model.
Sure. So like I said previously, we don't want to reinvent the wheel. So ideally, we don't want to start training from scratch. We have done that multiple times, but it's always a very large process and too large. So if we have the previous model that we think that is on a kind of like related domain, we want to fine tune that, or use a self-supervised model. Then once we have that, we will have to have some kind of labels just to tune the self-supervised model or the previous model. And those labels, we have to get them into the right geometry. So we have this kind of like back projection process. So we back project all of the labels to fit the solid geometry. Then, depending on the project, what we want to do, we're batching usually the images. Single image is too big of a unit to put into most of the different models. We're always trying to look at the literature, and we found some promising candidates, but just because of computational memory issues, we never managed to fit a high-resolution single image in a single model. So you have to work with batches. So we might want to batch into a monolithic dataset, or you might want to have an iterable dataset. So sometimes what we want to do is we have the sampler that have the sampler sample the satellite images towards infinity, and then until convergence, we just let it run. We start prototyping typically in a local machine with GPUs. I think that that's very valuable because it lowers the overhead of kind of like the code overhead. But at some point, the computational overhead will catch up with the code overhead when you start increasing the model complexity. So then we move into our MLOps platform in the cloud. And in there, we can just start doing stuff like grid searches and trying to find some parameters and running experiments. No matter what we think that we have learned, I still find that there is a very strong correlation between the number of experiments and the success of the model. So typically, the model starts working somehow on experiment number 30, and then it becomes useful on experiment number 60 or 70. Production models, we don't want to run them on the MLS platform. We have a different solution for that. So then we pass it into data engineering, and then they turn it into a product and harden it, and something that we control completely.
And in terms of the actual model development itself, too, I'm curious how much interference you have to deal with, where you're sending these radar signals from these orbiting satellites down to the ground. You're measuring the backscatter to figure out what are the actual interesting features and the topologies that I'm measuring. I'm curious if there are other kind of radio signals or radar sources that will potentially cause interference in that backscatter result, or some of the ways that you have to think about filtering out maybe out of phase information or information that is operating at a different frequency. Looking through some of the videos that ICEYE has on the overall SAR process, I know too that you have some frequency modulation that you do for chirping the signals to be able to get more information out as the satellite traverses over a particular range of its orbit. I'm just wondering kind of how much of that noise and interference you have to contend with in the process of trying to pull out this useful information.
Sure. We do have some RFI interference sometimes. So we attempt to filter it out, but sometimes it comes through. Typical example might be that if you're imaging a harbor, there might be a maritime radar in there, and if you get unlucky, it can take quite a large portion of the image and create an artifact that is not acceptable, and then you have to do something about it. Another one is that the images, they look like images to our eyes, maybe because we're so used to looking at stuff in the optical domain, but maybe a bad analogy is that the image it more resembles how a bat sees a world than how a human sees a world. So things are measured in distance and in time, more than distance and in time, and then the backscatter intensity more than like the analogs in the optical domain. This causes artifacts called ambiguities, because quite often two different things can be exactly the same distance from the radar, and that might cause a situation where it's impossible for the radar or the signal processing side to detect which is which. And then when you're looking at it in the image, you can have objects that are impossible floating in a wrong location, and those are ambiguities. Another example of that is that when you are compressing the SAR signal into these images, you are making this so-called zero Doppler assumption. So you are making an assumption that the thing that you are monitoring on the ground is going to be static, or it's not going to be moving. If and when you break that assumption, for example, if there is a train moving at a large speed, there will be a resulting displacement. We will not be able to geolocate the location of the train, and the train will appear in a different part of the image. So what this looks like for an outside observer is that it looks like that there's a flying train 50 meters away from the train track, and that's just something that it's not an artifact in the sense that it's something that we did wrong. It's an artifact in that sense that that's just how the SAR image works.
And then once you have the ML model, you're using it to generate outputs and flag certain features of interest. I know too that some of the output of what you're providing is some maybe map representations to show this is some of the physical damage that has occurred because of this wildfire, and we're able to detect that using the SAR imagery. But you don't want to have a human just looking at the raw SAR output because it's going to largely be incomprehensible. You need to put it into some representation that is understandable to human observers and kind of a human level representation of that. I'm wondering, what are some of the complexities that you have in terms of mapping some of the outputs of the machine learning models that you're building to a map, or a coloring a particular region of a map based on the feature detection that you're doing within the model, and just some of that kind of product level comparison between, I have this model, it tells me this one thing, now I need to figure out how to turn that into something that is understood by somebody who doesn't have all of this domain knowledge about SAR and geography and satellite imagery.
Yeah, models are not products. So in order for them to be useful, in order for us to sell them, we have to transform them into some ways. And here, if you're thinking about it, the compression ratio can be quite amusing. So if you're thinking about it, you have satellite images that's 2 gigabytes or something like that, and hundreds of millions of pixels. And what you want to do is compress it into an Excel table. So it might turn into a single column in an Excel table, and that's the resulting output. Quite often in machine learning, at least on our side also, it might be that we're only providing a partial answer. So we have a partial answer to a question, and then we have to do something else, sometimes something significantly different, in order for us to be able to use that in a product. So, for example, those I was previously mentioning those flood images. So we have this machine learning model that is turning our images into flood segmentation maps. But those in itself they will still have to be passed through other models in order to be able to use it in a product.
Given the fact that SAR data and even Earth imaging are still very niche domains that aren't kind of widely adopted throughout the industry, and a lot of the kind of technology space is focused on widely different problem spaces and data types, I'm wondering how that influences your ability to hire for open positions within your team, and some of the ways that you think about onboarding, as well as some of the ways that you think about how the work that you're doing can be propagated back out to other practitioners in the space, and if there's any sort of kind of open source policy you have around, these are some of the useful techniques that we have for data cleaning and data prep for SAR data. We want to make this something that is more widely adopted, and so we want to kind of ease the on-ramp for other people who are trying to solve adjacent problems within the same data domain.
For sure. Somebody with deep machine learning and SAR knowledge, that would be a unicorn. So typically people are missing either or. I think it's very, very expected and very healthy for people to have to spend some time learning the ropes when they join the company. Nowadays, it seems like that every SAR practitioner, everybody is trying to go into machine learning, or everybody is going to machine learning. So I think that will change with time. But right now, it's very expected that if you hire a machine learning engineer, most likely they will not have SAR knowledge. If they have Earth observation knowledge, that's already really great. There's like a quote from an astronaut that he was saying, it's easier to teach a geologist to be an astronaut than teach an astronaut to be a geologist. So in that case, I don't know which one is which. Is it harder to do machine learning, or is it harder to do SAR? But I do know that machine learning is getting much easier every year, while finding the right problem can be very hard. So if you want to have like pre-done images and then train a convolutional model to do something, it's so easy to find somebody to do that. But to find somebody that finds the right problems, finds interesting new approaches, can solve like hard technical stuff when the abstractions start to leak, that's very hard. Sometimes we're starting now to see the kind of flip side of that people can just import PyTorch and then you're done with it. Sometimes you see people that do have very advanced machine learning models, but they are lacking some of the fundamentals or the basics. So very advanced models, multi-stage models that do some very advanced stuff, but then lack the understanding of how the basic components of those models work. I'm very much an engineer by education, so I don't really mind. As long as stuff works, it's great. At the same time, if you don't understand the subcomponents, it's fine when stuff works, but when stuff stops working, you get some very intractable errors, some very complicated things that can take weeks or months to untangle.
And another interesting aspect of the problem space that you're working in is that it is potentially adjacent to other kind of 3D imaging approaches. I'm thinking in particular around capabilities like LiDAR, and then also some of the ways that your processing techniques for the SAR data can also be mapped back into computer vision and object recognition. And I'm wondering, what are some of the opportunities for cross-pollination between the work that you're doing and the work that's being done in things like self-driving cars, and then vice versa from things like LiDAR into the SAR domain? And, what are the areas where they're completely disjoint?
Of course, challenge breeds solutions. So if you have a hard enough challenge, it doesn't really matter what the challenge is about, because people will still have to innovate in order for them to meet that. So I would use maybe as an example the really great technology stacks coming out of Uber, or of course Facebook AI research, or people like that. Sadly, in the SAR, I can only think of it going the other way around. So we're kind of taking the lessons and not giving them. Maybe the closest analog field for me would be magnetic resonance imaging. They share quite a lot of kind of like the background of things that we are doing, and I really admire the way that they work effortlessly with the K-spaces. So they have a long culture of working in the frequency domain and doing work in there. Particular example would be I really enjoy the way that they do compressed sensing almost routinely. For them, compressed sensing, not meaning in the sense of trying to improve the resolution or something like that, because that always gets all of the old school Earth observation guys super angry. But I mean that in the sense that you try to take the best possible image given an imaging budget time. That's something that they do quite a lot in MRI, and I hope that at someday we could start applying some of those techniques to take the best possible SAR image given an image acquisition, limited image acquisition time.
And in terms of the work that you have been doing at ICEYE and working with SAR data and building ML solutions on top of that, what are some of the most interesting or innovative or unexpected ways either that you have seen ML approaches applied to this SAR data domain, or some of the most interesting or innovative or unexpected ways that you have seen the outputs of your ML efforts used for other purposes?
Sadly, when asked about the most interesting parts about in SAR, I wouldn't maybe answer machine learning yet. So machine learning for me, it's this is kind of like production factory and the scaling factory. Maybe the most important part, if I'm allowed to change the answer, maybe my most important part about the SAR imaging is the in-SAR. So that's what happens when you got this repeat track and you have these coherent images, and then you start getting the observation geometry so near each other that you can start taking into advantage the wave nature of this, or the longer wavelengths and the wave nature of these acquisitions. And because of that, you can start doing interferometric techniques. And by applying some of those interferometric techniques, you can start looking at features of height differences of sometimes millimeters. So you're in this situation that you are 500 kilometers above the ground in low Earth orbit, and you can measure tire tracks that appear in the middle of a field, or you can measure a herd of cattle moving around in a field because you can see their footprints from space. That's for me something that it has never lost the magic while I've been working with SAR imagery. And of course, nowadays there's quite a lot of people working with machine learning and in SAR, but that's quite a hard combination because, at least in my mind, machine learning has been historically better in getting this fuzzy ideas that the thing is approximately like this and being very robust about it. But it's quite hard to make machine learning models that are extremely accurate to the level that you need to be in order for looking at tire tracks from space.
Absolutely. And another challenge of any machine learning problem is the availability of data, which is something that is, I don't see that as being a problem for you in the company that you're at, since you are running your own satellites. You're doing massive scale collection of all of this information across the globe on a continuous basis. And I'm curious how much of that you're able to provide as a useful data set similar to kind of ImageNet for computer vision to help to encourage more people to start leveraging SAR data for different problems that they're trying to solve?
I would love to do that. It's above my pay grade, but I really need to pitch that. So one thing we do have is our SAR archive, and that by this point, the SAR archive is massive. And we are working right now on self-supervision, for example. And of course, it's a bit of a fashion topic right now, but I think if we would have a self-supervised baseline model available for the community, that would help a lot. I remember still being in the university and we were completely dependent on the company's data, and that would limit and bottleneck almost all of your projects. So that was one of the biggest improvements for me, is when you're working in the company and you have control over your own data generator, it takes the work to the next level.
And as you continue to build different models, you continue to iterate on the capabilities and the overall workflow. I'm curious, what are some of the near to medium term projects you have planned for ML applications at ICEYE, or any particular problem spaces that you're excited to dig into?
For example, the project I'm working on right now. So I'm working on self-supervision, and the idea is that as we have this large constellation of satellites, all of these satellites, they are slightly individual in the sense that their calibrations vary slightly. They are different ages, and then of course you have the situation that there's a very strong incidence angle dependency. So if you want to create classifiers or segmentation models, you have to have a very large amount of incidence angles, ideally all of them represented in the training data set. So because of that, when you're training something from scratch, you need a very large amount of training data, which is unfortunate. You don't want to reinvent the wheel every time. But we do have this archive, and we have the self-supervised models. So we can train a self-supervised model, and then we're going to use it as a backbone or fine-tune it or whatever we want to do with that. And that generalizes quite a lot better. A newer initiative, that's something that I've been trying, is that have a self-supervised model that you don't really train in batches, but something that you train continuously. So you're having it up on a cloud machine, and it's up there all of the time. Then it sees a data set, and the data set gets updated all of the time also. So as we get new acquisitions, we get new satellite images. Those satellite images are getting pulled into the instance, and then the instance is training the model continuously. The training never stops. And then when you need a new model, you can always pull the model from that instance, and you can use that model as the baseline model and expect it to represent the distribution of the satellites and the calibrations and the incidence angles happening right now quite well. So that's a project that is still deep into R&D phase, but something that I've been working on. I'm interested about.
And are there any other aspects of this SAR data domain and the work that you're doing at ICEYE and the different applications of ML for this Earth imagery with SAR data that we didn't discuss yet that you'd like to cover before we close out the show?
I think those were all the points that I wanted to make. Thank you.
Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest barrier to adoption for machine learning today.
The biggest barrier to adoption to machine learning today. Right now, you can see people are really smashing through the barriers. I don't think there are going to be a new AI winter. The opposite, things are overheating. So much people are coming into the field, and so much people are working on that. What I would like to see is the machine learning spill even more into different domains. So if you're looking at universities and research labs, all of the research labs, they're always starting machine learning groups, and the universities are starting machine learning groups. I would love to see more machine learning in materials science, for example. That's where the new ground is, and that's where the really exciting things will happen, I think, is that when they take not only necessarily the basic models of machine learning, but the approach of machine learning on iterating and the approach of machine learning on approaching a problem and generating and gathering data. I think very interesting things are going to happen.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing at ICEYE to bring ML solutions to this SAR data domain and the overall capabilities of Earth imaging. It's definitely a very exciting problem space. Definitely great to see the work that you and your team are doing. So I appreciate that. And I hope you enjoy the rest of your day.
Thank you very much. And thanks for having me. Have a nice rest of the day.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcast.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachinelearningpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachinelearningpodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.